Alright, this is the fourth video in chapter 15, and we're going to be talking about electrolytes and non-electrolytes. What are electrolytes? Electrolytes are substances that when they're dissolved in water, so you have aqueous solutions, are conductors of electricity. So electrolytes are substances that when dissolved in water will conduct electricity. We've talked about solutions conducting electricity before in this semester. We said in that chapter that it was the movement of ions in water solutions that were known to conduct electricity. This is how ions were discovered through some conduction experiments in water solutions. So, what are these compounds that are forming ions when dissolved in water? There are three classes of substances that can dissolve or react with water to form electrolytes: acids, bases, and salts. So acids, bases, and salts all go together because they are electrolytes. They dissolve or react with water to produce ions in solutions, and we know that ions are what conduct electricity. So acids, bases, and salts conduct electricity because they form ions in water. They are electrolytes. So are all electrolytes created equal? Do all compounds, when dissolved in water, generate the same current? The answer is no. Electrolytes can be subdivided into two different categories: strong electrolytes and weak electrolytes. So which is which? Strong electrolytes are substances that when they dissolve in water, or ionize in water, I should say, react with water or dissolve, we'll talk about that in a second, are 100% ionized in the water. That means they completely either react with the water or they completely dissolve in the water to form ions completely. The reaction or the dissolution is complete. Strong electrolytes are strong acids, strong bases, and any salts that we would say would be soluble in water. So sodium chloride, for example, is an example of a soluble salt. It it dissolves in water to form sodium ions and chloride ions, and it dissolves completely. It's not partially soluble, it is soluble. So they completely ionize in water. If I was going to put some substance into water, so if I have a substance plus water, and I want to say that it completely ionizes, I'm going to use a completely forward arrow in that chemical reaction. So 100% ionization is achieved. So strong electrolytes are strong acids, strong bases, and soluble salts. Now, what are strong acids? Well, these are typically memorized by chemists. You would probably have a list. In your book on page 345, there's a table in your text. It says a representative electrolytes, non-electrolytes. So how do you know which acids are strong acids? Remember, acids always start with hydrogen. They're dissolved in water, aqueous. There are things like H2SO4, sulfuric acid, hydrochloric acid, nitric acid, acetic acid, HC2H3O2. Those are the acids that are going to be the strong type acids. There are others as well. As far as bases, what are some strong bases? Sodium hydroxide is a strong base. There are others as well. Sodium nitrate is an example of a soluble salt. Sodium chloride is a soluble salt. Any of the soluble salts, you can use the solubility chart for that. So those are going to be some examples of some strong electrolytes. There are others as well. HBr is a strong acid. Calcium hydroxide is a strong base. Barium hydroxide is a strong base. If you go to table 15.3 on page 347, you can see a complete list of your strong electrolytes. There's another list. So there's two tables of electrolytes in your book. I accidentally misspoke when I said that acetic acid was a strong electrolyte? It is not. It's a weak electrolyte. My apologies. But those are examples of strong electrolytes because they completely dissolve in solution. If you had a list of strong acids and strong bases and soluble salts available to you, you could say, okay, because that's a strong acid, I know that it is going to completely dissolve or react in water. What are weak electrolytes? Weak electrolytes are less than 100% ionized or dissolved in water. Typically, these are going to be your weak acids and your weak bases. Things like acetic acid, carbonic acid, sulfurous acid, hydrosulfuric acid, ammonia, NH3, the base. So, weak acids and bases are weak electrolytes. They do not completely ionize or react with water. If we put that substance into water, instead of fully reacting, they would only partially react. So remember, when we put the strong electrolytes in water, I said that they fully react to form ions in the water. But these will only partially react. So weak electrolytes, less ionization occurs. So the current that's produced is less as well. Now, do all compounds dissolve in water to form ions? The answer is no. Not all compounds that you put into water will react or dissolve in water to form ions. If they don't do this, they are called, substance does not form ions, it's called a non-electrolyte. A substance that the aqueous solution is a non-conductor. It's everything that's not an acid, not a base, and not a soluble salt. So if something's insoluble, obviously it's not going to form an aqueous solution. It's a non-electrolyte. Things that dissolve in water that do not form ions. Things like glucose. Glucose or sugars. They're not acids or bases, but they just dissolve in the water. So they would be examples of non-electrolytes. There are plenty of examples, though. So electrolytes react with water or dissolve in water to form ions. They completely react, then they're going to be strong electrolytes, like strong acids, bases, and salts. If they weakly react, partially, they're going to be weak electrolytes. Once again, if you want to find a chart of all the acids and bases that we consider strong versus weak electrolytes, you can look on page 347 in your text for a representative example of a list when you're doing your homework. So then, how are the ions formed when you put a solute into water? There's actually two different ways that charges or ions form in solution. The first way is something called dissociation. It's not disassociation, it's dissociation. People often misspell that. The other process is ionization. So we have dissociation versus ionization. These are two different ways that ions can form when the solute's dissolved in water. So what is dissociation? We'll start with that first. Dissociation is basically dissolution. It's the breaking apart of the two different ions in a salt whenever they're dissolved in water. So dissociation has to do with dissolving a salt. We know that a salt is another word for an ionic compound. In ionic compounds, the ions already exist in an ionic compound. They're just held together tightly by these coulombic opposite charges. So, for example, for sodium chloride, if you have a solid crystal of sodium chloride, it's got many sodium ions and many chloride ions that are held together tightly and they're bound. When you dissolve sodium chloride into water, the sodium and chloride ions dissociate or break apart. So when we say that the sodium and chloride ions dissociate, if the sodium ion and the chloride ions in the solid state are originally bound together by these really strong, attractive forces. When they're put into water, remember water is a polar molecule. Remember, it's got a bent shape in its three-dimensional structure, and the oxygen is more electronegative than the hydrogen. So remember how we said that oxygen's negative and hydrogens are positive? And we said that this was called a polar compound because there's directionality in the water molecule's charge. There's a negative region and there's some positive regions. Well, because of the negative and positive regions of the polar compounds, those charges in the water particles can interact with the charges of the ionic compound, and it dissolves the ionic compound. What happens is, we say, what was the word we use? The ionic compound dissociates, meaning the cation and the anion are broken apart or pulled apart as the water molecules dissolve them. We would say the ions become hydrated in solution. So let's go back and look at this equation now. If you start with a solid that's soluble in water, when you put that solid into water, we say it dissociates, right? Dissociate means to break into the ions into their aqueous hydrated phases. So notice we've shown dissociation here. We've ionized the compound into the sodium cation and the chloride ion. We've noticed that we've gone from solid to aqueous because now they're dissolved in water. So NaCl is dissociated when it's dissolved. So clearly we've created ions in solution because now they're free-flowing ions. They're electrolytes. Let's do calcium chloride here. Calcium chloride is CaCl2. Whenever this compound dissolves in water, we have a calcium cation with a +2 charge, and we have how many chloride ions? We have 2 chloride ions for every calcium cation. So here's a chloride, and let's say here's a chloride. So the 2 chlorides with -1s counteract the positive calcium with a +2 charge. So this would be the solid state of the ion in simplest form. The salt is all solid held together. When we put this compound into water, it dissolves in water, so the ions dissociate from one another, and the calcium ion is freed from the chlorides. How do we show the dissociation is a chemical reaction, a process of ionizing? It's dissociated. We write that the calcium ion has been dissolved in water, so it becomes aqueous, and the chloride as well. The chloride becomes aqueous, but how many chlorides are there? There's 2 chlorines in every 1 salt unit, so we have 2 free-flowing chloride ions. How come I didn't write Cl2-? Those chlorides are not bound together as a molecule, but they're separated, right? So because of that, I write 2 chlorides. So whenever you have a subscript and you ionize it, bring that out to the front. Here's another one, potassium hydroxide. Potassium hydroxide dissolves in water, and it forms a potassium cation, which is aqueous, and the hydroxide ion, which is aqueous as well. So we have the cation and the anion. All right, so salts that are soluble in water dissociate. Aqueous, that means that those ions are free-flowing in solution. They've been hydrated. The second mode to produce charges in solution, we said, was the mode of ionization. So if dissociation is by dissolving, we're not reacting with the water, it's just dissociating the ions. Ionization is the product of when you put a molecule in water, it needs to chemically react with water. Remember, molecules do not have full charges because they are bound together by sharing electrons. So in order for ions to form in water, the molecule literally has to react with water. And we've shown, this is what we've shown before. We know that acids ionize in water because acids have to chemically react with water. They are usually molecules. Hydrogen is a nonmetal, and it's always bound with some other nonmetal. For example, HCl is a molecule. It only contains nonmetals. So it's not an ionic compound. It doesn't dissolve in water. It reacts with water. And when it reacts, This is Bronsted-Lowry reactions, or you can think of it as Arrhenius, but Bronsted-Lowry, the proton transfer. Acids will lose protons, and they will become more negative. The base will gain a proton, it will become more positive. And we talked about that previously. So we form ions by chemical reactions in solution. If an acid's a strong acid, like hydrochloric acid, we say it fully ionizes. We use a completely forward reaction arrow there. And I messed up here when I wrote it. But for example, here's another example of an acid. And this is phosphoric acid. And phosphoric acid is not on the list of strong acids. It's actually a weak acid. Weak acids, we said, were weak electrolytes. They don't fully ionize when they react with water. So we use an equilibrium arrow in the chemical reaction showing the reaction. So, something to think about here. When you have strong acids, you will always fully ionize. You'll use the full ionization area. It will completely react. But when you have weak acids, it's not on the strong acid list, it will only partially ionize or partially react, so you're going to use your equilibrium arrows. Same thing is true with weak bases. The only weak base we're actually going to use in this course is NH3, ammonia, or nitrogen compounds that are neutral. NH3 is ammonia, and it's a weak base. It's on your weak base list. We know that weak bases are weak electrolytes, so they will only partially ionize in solution. So we're going to use, once again my arrow's messed up, when this base reacts, what do bases do? They're proton acceptors. It will become NH4+, but that is a partial reaction. It's an equilibrium reaction. It's not fully going to ionize. So the bigger picture here is you got to be able to put everything together. What is an electrolyte? Electrolytes, we have two types, strong and weak. We know that soluble salts, acids, and bases are electrolytes. Soluble salts, strong acids, and strong bases, if you're given those lists, will always fully ionize. And weak acids and weak bases will only partially ionize. You'll get the equilibrium arrows. So these are the two ways. If you have a salt, salts dissolve in water or they don't. They will always dissociate. Strong bases, where are they put on the list? Well, strong bases are things like sodium hydroxide and calcium hydroxide. Those will actually be found on the dissociation list because they are ionic compounds. Alright, now it's time to kind of test ourselves. Let's put all of these concepts that we've been studying so far to use. Now, I will say that I'm going to be using the chart in your book on page 347. At the bottom of the tape, there's table 15.3. It contains a list of strong and weak electrolytes, or strong acids, weak acids. This problem says to complete the acid-base reactions below. So we know we've got an acid mixed with the base here in each problem. It says indicating partial or full ionization, so whether or not we're going to partially ionize or fully ionize, using reaction arrows. It says to label each compound as an acid, a base, a conjugate acid, and a base as well. So let's put it all together. Alright, so the first one we have here is we have sulfuric acid plus water. Now, we know water is a neutral compound, but it's amphoteric. It can act as an acid or a base. And so each of these, we want to know, is water acting as the acid or the base? In order to find that out, let's look at the other compound. So the first one is sulfuric acid. Obviously, we probably know since it's called sulfuric acid, it's going to be an acid. So this is our acid. It has a hydrogen at the front. So the water then must be reacting as the base in this compound. In this reaction, I'm sorry. Okay, so sulfuric acid reacts with water. Now, what type of acid is sulfuric acid? Sulfuric acid, on your chart, H2SO3 is found in the weak electrolyte side of the chart on page 347. So we know that this is a weak acid. Why is that important? Well, weak acids are weak electrolytes, and they only partially ionize in water. So we're going to use a partial ionization or an equilibrium arrow. This reaction will occur, but the reverse reaction will occur as well. We won't get complete ionization. All right, now it's time to put our thinking caps on. Can we remember what we've talked about with acids and bases? We're going to be looking at Bronsted-Lowry acids and bases. And according to Bronsted definitions, acids are proton donors, which means they lose a proton. So if this compound loses a proton, H2SO4, if it loses H plus, it's not going to be H2. If it loses an H, it'll be HSO3. I think I said 4, I meant 3. It'll be HSO3. Now if it loses H plus, it not only loses a hydrogen, it loses a positive charge. So it's neutral right now, and we lose a +1 charge. What is 0 minus +1? Well, obviously it's -1. Remember how I said acids become more negative? Think of it that way. Acids lose protons, so they become more negative. So what is this compound called? If the sulfuric acid was the acid, then the hydrogen sulfite is the conjugate. Sorry, my screen's not working. All right. So hard to write with this pen. It's the conjugate base. Acids produce bases, and bases produce acids. You get your conjugate acid-base pairs. All right, so if water's the base, remember by Bronsted-Lowry, they're proton acceptors. So it's going to gain H+. So the base will produce the conjugate acid, H3O+. All right, so H2O becomes H3O+. Hydronium ion. By the way, if you ever produce a hydroxide or a hydronium ion's always an acid. Never label that a base. And hydroxide is never an acid, it's always a base. So if you always know what the acid and base are, you can kind of find your way around the system. All right, let's look at the next one. So there's the first reaction. We transferred a proton and we got all that. The second reaction here says hydrobromic acid plus water. So HBr plus water. Once again, we have an acid here. It's HBr. If you look on your list, though, HBr is listed under strong electrolytes. So this is a strong acid. Why is that important? Well, we know that strong acids are strong electrolytes and they fully ionize. So I'm going to use a forward arrow. So hydrobromic acid reacts with water. This must be the base. So acids lose protons, they become more negative. So HBr minus a proton becomes Br minus. That's going to be the conjugate base of that acid, bromide. And then the base, the water once again, will form the conjugate acid. So water gains a proton, we'll have H3O+. So we have, once again, our proton transfer. This is a full ionization reaction. It completely occurs, though. All right, let's look at the last one. We have ammonia. Ammonia is NH3, by the way. So it's not ammonium, it's ammonia. That is always going to be a base. So that's a weak base. Water then is going to act as our acid. So it's a weak base, it's on the weak electrolyte list. So when it reacts, it partially reacts. What do bases do? Bases are proton acceptors. So NH3 will become NH4+. And NH4+, if the NH3 was the base, NH4+ is the conjugate acid, right? All right. Water this time, remember, water is amphoteric. It can act as an acid or a base because it's neutral. It can gain or lose a proton. So water this time is going to be an acid. Acids lose protons. So H2O becomes OH minus hydroxide, which we know is a base. So this is the conjugate base of our acid. So here we go. Now we have our final reaction. The weak base plus acid equals the conjugate acid plus the conjugate base. Alright, so that's putting a lot of this weak electrolyte, strong electrolyte, Bronsted-Lowry acid base stuff together. Alright, hopefully you should be able to do this kind of work by the end of the chapter. So since we're talking about acids and bases reacting together, there's a very, very important reaction type or subcategory that you need to know called a neutralization reaction. When acids and bases react together to form salt plus water, this is called a neutralization reaction. It usually occurs when a strong acid reacts with a strong base. So if you ever notice that you have a strong acid and a strong base mixed together, not a strong acid in water or a weak base in water, and so on and so forth, but you have a strong acid plus a strong base, or a hydroxide base, and your products are salt and water. Remember, water is neutral, and a salt is not an acid or a base. So what you have is a neutralization reaction. You start with things that are acidic and basic, and you end up with a neutral solution. Now, this is actually a type of double replacement reaction. When did we study these? We studied double replacement reactions not too long ago on the last test in Chapter 8. So if you want to go back and look at double replacement reactions in order to predict products for this a little bit more, you can go back and review Chapter 8 if you wish. But let's look at neutralization reactions. Here's an example. Here we have hydrochloric acid. That's a strong electrolyte, it's a strong acid. We're reacting it with sodium hydroxide, which is a strong electrolyte, it's a strong base. So we have strong acid plus strong base. Well, remember that if this is a double replacement reaction, we have cations and anions in each of these compounds that we can kind of draw. Remember, in a double replacement reaction, the cations switch places with the anions. So the hydrogen and the sodium switch places in a double replacement reaction. So instead of hydrogen with chloride, we're going to have sodium with chloride. So I'll have sodium plus with Cl minus, and then instead of sodium with hydroxide, I'll have a hydrogen ion with hydroxide. H plus OH minus. Alright, let's take a closer look at what we have. The cations have switched places with their anions. So sodium and hydrogen have switched places. Remember, whenever you do a double replacement reaction, you always keep the charges of the ions constant, and you need to rebalance the charges. So the first thing I did over here on the right-hand side of the equation is I wrote the charges. Like I have a sodium. Sodium's a +1. It's in group 1A on the periodic table. Chlorine is -1. It's in group 7A on the periodic table, so 7 minus 8 is -1. I did the same thing with hydrogen and hydroxide. Now I'm going to go back and I'm going to do the crisscross method where I balance the formulas to give me my neutral compounds. So we have sodium and we have chloride, and we have a +1 and a -1, so they balance out completely perfectly. So when I go to write sodium chloride, first of all, is that soluble in water? It is. If you use a solubility chart, you can find one in the appendix of your book. Let me look real quick to see where it is. Appendix. Let's see here. On page A16, appendix number 5, the solubility table. If you are ever wanting to write a complete equation and you wanted to find out if a salt is soluble in water, you can check out appendix page A16. It's appendix 5 in the back of your book. There's a solubility table there. Alright, so sodium chloride is soluble in water. Now what have we made here? HOH. HOH is the same thing as what? It's the same thing as water, so I'm going to rewrite that. Once you switch your cations with your anions, you can always go back and balance the formula first. And HOH is the same thing as water. Now, does water dissolve in water? No, water is just more water. So here we have two aqueous solutions. When they're dissolved in water, they form more water, and they form sodium chloride, which is soluble in water. So let's look at what we've done here. We started out with hydrochloric acid, that was our acid, and then we reacted it with, so a strong acid, we reacted it with sodium hydroxide, which is a strong base. We formed sodium chloride, which doesn't have a hydroxide, it's not ammonia, and it's not an acid because it doesn't have a hydrogen ion in it. Sodium chloride is an ionic compound that's soluble in water. It's a soluble salt. We formed the salt, and plus we formed water. So this reaction is an example of a neutralization reaction, because neutralization reactions are always reactions where an acid plus a base yields salt plus water. Okay, so anytime you have an acid and a base forming salt and water, you go, hey, wait a second, that was a neutralization reaction. I didn't end up with acid or base in my product. Alright, let's do another example. Here we have sulfuric acid plus magnesium hydroxide. So once again, the cations are going to exchange places with the anions. So my cation, the hydrogen, has a +1 charge. What is sulfate's charge? You can, if you want, you can reverse the crisscross there. But sulfate, hopefully you'll remember, is a -2 charge. Alright, magnesium, group 2A on the periodic table, has a +2 charge, and hydroxide is a -2 charge. Alright, so we're going to switch cations, switch places with our anions. So instead of hydrogen sulfate, sulfuric acid, we're going to have magnesium sulfate. So magnesium is +2. That's why I wrote it there, so I would remember I need to write my charges so I can balance the formulas first. Remember, when you do double replacements, always balance the formulas, then balance the equation. So I've got magnesium with sulfate. I love magnesium sulfate. Okay. MgSO4. Now notice I have a +2 and a -2. Do I need to balance that further in the formula any further, or is it backwards? No, it's already balanced as written. So we have magnesium sulfate. Is magnesium sulfate soluble in water? Well, I'm staring at my solubility table right now. I've got magnesium. I've got sulfate. I've already lost it. It is soluble in water. In the appendix, I looked at that. So it's aqueous. So we have a soluble salt. And what else do we form? Hydrogen is now going to form with water. So we have HOH, H plus, H minus. How do I write HOH? Just rewrite that. It's water. It's H2O. And water is a liquid. Okay, it doesn't dissolve in itself. It's not aqueous. It's a liquid. Alright, so I'm going to go back. Remember, always do these things in pencil. You will regret it if you don't. Alright, so we have sulfuric acid plus magnesium hydroxide. Hydroxide salts are bases because they contain hydroxide. Yields magnesium sulfate. That's a salt. It's neither an acid nor a base, but it's soluble salt. And we have water. This is a neutralization reaction. Now, one thing I didn't do is I didn't go back and balance the equation. Remember, balance the formulas, then balance the equation. Let's see, 1, 2, 3, 4. So I need a 2 in front of here. 2 oxygens, sulfate. There we go. Now I think we are balanced now. Alright, so I think you get the idea. I'm not going to do this forever. You can do this with any acid and base that makes a salt and water. It's called a double displacement reaction. The special name is a neutralization reaction. What's really going on inside of here? Well, in the next video, we're going to talk about something called writing net ionic equations. And we're going to see what the reaction is behind neutralization reactions. So we're going to figure out how to solve net ionic equations by ionizing our compounds. We're going to do total ionic equations and then net ionics to see what's really going on in these chemical reactions. Not everything is reacting.